I can do binomial CDF n comma p comma number of success. But now what does this compute when I'm doing the cumulative distribution function? This computes the probability of 0 successes up to that number of successes. So if I did say binomial CDF of 15, 1/6, and 7, that would compute the probability of 0 successes, 1 success, 2 success, 3 successes, all the way up to 7 successes, and add all of those together. But now the problem is with what I want to compute, I want to take away 0 successes and 1 success because I'm starting with x being 2. So I'm going to subtract out the binomial CDF of 15, 1/6, comma 1. So I'm subtracting out 0 success, the probability of having 0 4s or 1 4.
There's no way to combine those two?
There's no, so if we heard that question, Sam just asked, is there any way to combine those two? On the very new calculators, there might be, but I think that on most TI-83s and 84s, there's not a way to combine those, and you just have to do it as two separate calculations. So it's not like, if I was doing the normal distribution, I would just do normal CDF, the first z-score to the second z-score, and be done with it. But for some reason, they didn't write the program for the binomial cumulative distribution function that way, where I could just give a starting point and a stopping point. Seems silly, but apparently it was easier to program this way. So someone just did the calculation for me, and it's the probability that we have between 2 4s and 7 4s is about 74%. So now let's think about expected value and variance and standard deviation. So clearly, if I'm rolling the die 15 times and I'm just looking at the number of 4s that I can get anywhere between 0 4s and all 4s and 15 4s. So there's only 16 possibilities for this random variable. So I could, if I wanted to find the mean of x, I could just compute the sum of x times p of x, because there's only 16 options, so I could just use binomial PDF to make a table here on the calculator and do that. But that would be a little bit tedious, and it would be especially tedious if I wanted to change the number of Bernoulli trials to say like 18,000 rolls of the die. Then I'm certainly not going to make a table with 18,001 entries on it. So luckily, our intuition kind of serves us well here, is that if I'm rolling the die 15 times and the chances of getting a 4 are 1 out of 6, then I'm probably just expecting 1/6 of 15. I'm probably expecting that many 4s. And that's, if you actually rig through the math on Saturday night when you're bored and you're looking for something fun to do, it actually works out nicely when the distribution's binomial, that the expected value is just n times p. So notice that the thing to keep in mind here is that formula always works. That's always the formula for the expected value. It only simplifies to this if your random variable is binomial. So one thing that we have trouble with is that I'll see people on the midterm computing expected values by just like taking some number and multiplying it by some probability, because like they've seen the binomial calculations. So this doesn't work all the time. It's just for if the random variable is binomial. So in this case, the expected number of 4s would just be 15, 6, which is what? 6 goes into 15 2.5 times. And remember, the expected value, the average of your random variable, it doesn't have to be a value that the random variable can actually exist at. So x, it's impossible for x to be 2.5. This is an average. That's totally fine. So 2.5, I should label my variable here. This is 2.5 fours in 15 rolls on average. Okay, so what about variance and standard deviation? So again, I know that the variance of a random variable is the sum of x minus mu of x squared times p of x. That I do those calculations and then I sum over all of my all those possibilities. So again, the math works out very simplistic here. This is always, that's always how you can find the variance. But if the random variable is binomial, it works out very nicely. It's n times p times 1 minus p. And you'll notice that you can denote 1 minus p as q. The book does that. So I see a lot of people doing that. That's only if x is binomial. So that means the standard deviation for the binomial distribution would be n p 1 minus p, the square root of that. So in our case, that would be 15 times 1/6 times 5/6. Then we're going to square root all of that. And so that's the standard deviation is going to be 1.44 fours in 15 rolls. And I need to make a slight change here. Someone, oh no. I don't know if this is going to mess up. Oh dear. Okay, this should be an x, not a 2. That should be mu sub x. Great, so we've done some computations involving the binomial distribution. And now let's look at the geometric distribution. So let's just compute a probability straight off the bat. Let's compute the probability that y is 4. Well, we've used a lot of 4s. So could I possibly erase that? Oh, sweet. That worked that time. Let's compute the probability that y is 3. So remember, this video is getting a little long, so if we think back to like 15, 20 minutes ago, we defined y to be how many times you roll the die, and once you get a 4, you're going to stop. So that means if y is 3, that means I rolled the die 3 times, and on the 3rd time I got a 4. On the first 2 times, I had to not get a 4. So that means there's only one way for this to happen. I have to not get a 4 twice, so it has to be not 4, and not 4, and 4, in that order. So that would be 25 out of 216. If that is really 6 cubed, I think it is. I think I did the math right there. So the geometric random variables are very nice because I don't have to worry about combinations counting the orderings, counting all the possible orderings, because for any given value in this geometric distribution, there's only one way for that value to happen. You get a string of whatever you're denoting failures, which is in this case not a 4, and then once you get that 4, then it's over. So if I did something like, what's the probability that y is less than or equal to 5? So what would that look like if I start writing it out? Well, if y was 1, that means I got the 4 on the first roll. What about if y was 2? That means I missed the 4 on the first roll, got the 4 on the second roll. What about if y was 3? That means I missed the 4 on the first 2 rolls, then I got the 4. We kind of see a pattern emerging here. I can do a little plus dot 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 and cut right to the end, which would be not getting a 4 times in a row, and then on the 5th roll, getting that 4. So again, I can use the plus dot 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 to kind of cut out the intermediate sort of writing out all of the probabilities. Now, thankfully, there's a nice way to do this on the calculator. We can do here, instead of adding up all these individual probabilities, evaluating this long string on the calculator, we could just do a geometric CDF, which is going to be P, comma, the number that you want to end at. So in this case, if I did geometric CDF of, say, P is 1/6, that's my probability of success, and I want to go all the way up to 5, that is the same exact thing as all of this written out here. And I'm just going to pause for a second while somebody does this for me on the calculator. Oh, already got it. That's about 60%. It's about 0.60. So the only thing you got to be careful about is that sometimes with geometric probabilities, you've got to work with the complements unless you want to get into some fancy infinite sum work. So I wanted to do something like the probability that y is greater than 3. Well, think about this. That means that the first success, the first 4, would come on the 4th roll, or the 5th roll, or the 6th roll, or the 7th roll, plus dot, 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 all the way out to the 50th roll, plus dot, 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 all the way out to the 867th roll, plus dot, 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 going on forever. So this would never end. This would be, so I'd start with the 4th roll that I'm going to miss 3 times and then get that 4. Then it would go maybe 5 rolls plus dot, 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 dot. That sum would keep going. Now I could actually evaluate that sum, because I think I could factor out the 1/6, and then I think I'd be left with an infinite geometric series that converges because the ratio is 5/6, which is less than 1, and I could go through some fancy math. But it would be much easier to just write the probability that y is greater than 3 is the same thing as 1 minus the probability that y is less than or equal to 3. And then that I can just easily write out and compute as a geometric CDF. So the complements really work nicer here. And thinking about the expected value, again, I don't want to do this. I mean, that's the formula that always works, but there's an infinite possible number of y values here in the distribution. So I just want to kind of think about this. If the probability of getting a 4 is 1/6, how many times am I going to have to roll before I end on that 4? Probably 6 rolls, because there's a 1 out of 6 chance of getting a success. So it'll probably take about 6 rolls to get a success. So the expected value is just the reciprocal of the probability of success. Just be careful, that's only if the random variable is geometric. So in this case, that's 1 over 1/6, which is about 6 rolls. So I think that's enough that we can start doing problems. And that gets us through most of chapter 17, and we'll probably come back and make another video soon.